This is The Future Of, where experts share their vision of the future and how their work is helping shape it for the better.
I'm David Carston. Earlier this year, an asteroid was briefly predicted to have more than a 3% chance of colliding with Earth, the highest impact risk ever recorded for an object of its size. That chance has since dropped to below 1%. But what if next time it doesn't? What exactly would we do? And who's working behind the scenes to keep us safe? Well, today I was joined by Associate Professor Nicholas Timms, an expert in rock and mineral deformation and geochronology, and Professor William Rickard, Director of Curtin's John DeLater Centre, home to some of the most advanced analysis tools on Earth. In our chat, we discussed exciting new discoveries by Curtin scientists and how ancient space rocks could hold the key to protecting our planet's future. If you'd like to find out more about this research, you can visit the links provided in the show notes. Nick, to begin with, can you walk us through how extraterrestrial geology became a part of your career?
Yeah, for sure. So my expertise, I guess, is analyzing samples. So samples that have come from Earth, usually, as my career has progressed as a geologist, but extraterrestrial samples became kind of part of my life, I guess, 2007, I think it was, a long time ago now. And it was a colleague of mine in Curtin who basically handed me a sample that he was having a lot of trouble with understanding, and he asked me to analyze it using the fancy equipment and the expertise that I have. And I said, okay, what's the nature of the sample? He said, oh, this is a piece of the moon.
No.
Right, so...
Mind immediately blown?
Yeah, mind immediately blown. It was then the first time I'd, held a piece of moon in my hand, but since then I've worked on all of the samples that were collected from the Apollo missions, every single mission, and it's extended to all of the samples that have been returned to Earth by various space missions, and as well as still analyzing geological samples from Earth as well. So it was a kind of a pivotal moment for me, and it just got me excited and into this whole thing to do with planetary science and analyzing extraterrestrial materials to find out what we can find out about our solar system much, much further than I'd ever thought before, just thinking about how the Earth works as a geologist.
Nick, your research also touches on planetary defence. Now, can you explain planetary defence for us and tell us how real the threat of asteroid impact actually is?
So, yes, there are potentially hazardous asteroids out there, near-Earth objects that have got that have been discovered out there in the solar system that have got orbits which are Earth-crossing, or they come close to Earth. And the clever people who work out those orbits also give a probability of those objects hitting Earth. In the early days of discovery, like the one from last year, I think that one had a 3% chance of hitting Earth, and that was very early on before they had really fine-tuned the orbit. I think there's a lot less now, but there's quite a big list of potentially hazardous asteroids out there. And the field of planetary defense is all-encompassing insofar as finding those asteroids, understanding those asteroids and objects, figuring out what the hazards are and trying to mitigate those risks in different ways to basically either see how we can redirect them or nudge them out of the way so they don't hit Earth and don't cause a problem for humans or life on Earth as we know it.
Can you tell us about some of the missions that have actually returned asteroid samples to Earth and how geologists like yourself are involved?
There have been a few missions by different space agencies to some of these near-Earth objects, some of these near-Earth asteroids, to actually collect samples from their surfaces and bring them back to Earth. There have been 3 so far. Some by the Japanese Space Agency, who are very pioneers in this, and then one more recently by NASA called the OSIRIS-REx mission, which went to an asteroid called Bennu and landed in 2023 and brought us by far the largest sample of asteroid that's ever been collected. And here at Curtin, we've got a team of scientists who are privileged enough to be on the science team as mission scientists to actually analyze those fragments of asteroid that were brought back. And so I'm a part of that whole mission and have been diligently analyzing some very small particles of this asteroid material since they've been returned.
Will, Curtin's John DeLater Centre houses some of the most advanced tech on Earth. What role do these tools play in helping Nick analyse those extraterrestrial materials?
Yeah, absolutely. Yeah, the John DeLater Centre at Curtin University is well equipped with some really state-of-the-art instrumentation. So when we want to study these really precious materials, we have such a small amount that comes back to Earth. Curtin University is very fortunate to have a beautiful record over a long period of time to do quality science with this material, and so we get some of this material by being part of these sample analysis teams. And then, but NASA and Japanese Space Agency or Chinese space agencies or European space agencies, they want the most amount of information from the smallest amount of material and to do the least amount of damage. So we've got to have the best tools to be able to extract that information, and it's got to be really, really accurate. So we have optical microscopes, we have electron microscopes, we have X-ray analysis equipment, laser equipment, mass spectrometry, all these different tools. And we've designed a kind of workflow where we can go from the macro scale and all the way down to the atomic scale. We have a tool called atom probe tomography, which we can extract the atoms off the sample almost one by one and reconstruct that in 3 dimensions to get absolutely all the information we can. And so we do that to try understand the chemistry, the microstructure, but also the isotopic composition. So that can tell us how old the sample is, the provenance, where it may have come from, other parts, what it was a parent body that this material was from. So yeah, they're a wealth of information, but it requires state-of-the-art instrumentation to extract that.
I guess that combination of instrumentation, does that make you, does it make Curtin or the John DeLater Centre a sought-after, destination for some of this sample material as far as the agencies are concerned? Do they look to the JDL as the place to go?
Absolutely. I mean, we don't get these samples just because we put a hand up. These samples come to Curtin because they have that combination of world-class experts from Earth and planetary science, but also within the John DeLater Centre, and world-class instrumentation. So having that combination of the know-how and the tools to do that is why we've got a reputation to be able to do it in the past, and this is why we get involved in these missions. And yeah, it's a team effort. It's a lot of work, but when you put in a sample in an instrument and you straight away you're looking at things that people have never seen before. There's minerals there that have never been studied before. You never know what you might see the next day. That's really exciting.
Nick, the analysis on the asteroid was called Bennu.
Bennu.
Yes, Bennu. That wasn't necessarily for planetary defence, but nevertheless there was some exciting discoveries. Tell us about what you uncovered.
So Curtin University got some of the earliest samples from that mission as they were gradually opening and revealing what was returned. And there was some talk of whether there was any contamination from the Earth in those samples. So they sent us some samples really early on to look at, and we had a look at them under our electron microscope and some other equipment as well. And we discovered salt. Sodium chloride, the same kind of stuff that you put on your chips. Salt in meteorites, so rocks that have come from space and made their own way here, is really, really rare. To find salt in a sample that is being brought to Earth in a spacecraft and remain pristine, hasn't seen the atmosphere of Earth, hasn't been sitting on the ground with water and so on, was really special. It just it provided a window into what it's like on these asteroids, or what it used to be like on these asteroids billions of years ago. And it was the first discovery amongst many other discoveries by the international research team of different salt-like minerals, the kind of things that you get on a salt lake out in West Australia bush today. That was a really good indication of what the environment was like at some point on what we call the parent body, the space object, like a baby planet, I guess, that the asteroid Bennu was formed from bits of. Because we can see salt and all these different kinds of salt minerals on there, we can get a sense of what kind of temperatures and what kind of fluids were around on that body. And that's super, super important. Not because it's a nice story, it's because colleagues elsewhere, other colleagues on the sample analysis team who are specialists in looking at organic materials, found a huge range of organic compounds, all different building blocks of life, prebiotic organic material. And on Earth, at least, salt or salty environments, briny environments, are places where organic material can develop and polymerize and thrive. So we can couple, our findings with their findings and have a window into the fact that this, proto-planet had all of the right ingredients for forming life. We haven't found life, but it was all there. It was all set really early on in the solar system, which is a really intriguing kind of story.
Going back to planetary defence and the notion of a strategy should an asteroid collide with Earth in the future, a meteorite landed in the Western Australian wheat belt on Mother's Day. Can meteorites teach us anything in relation to planetary defence?
Absolutely. So we're calling it the Mother's Day meteorite for obvious reasons. If you're around in Perth or in the Western Australian region, generally in 6 or 6:30 in the morning, I forget exactly when, and you saw a huge fireball streak across the sky, that was a meteor coming in, and eventually at the end of that, dropping stones which are part of that, fragmented parts of that meteor. And this is what we're calling the Mother's Day meteorite. And it's important to try and get those samples really quickly because they can become contaminated from Earth. And that contamination can change the rocks, a bit like rust can change, your car if it's, left too long next to the ocean. So we want to collect those meteorites as quickly as possible after they've fallen so they don't change their properties. And if we can collect them fast enough, we can, look at exactly what their fingerprint of composition of what kind of object it came from. We can track where the fireball came from and predict what its orbit was around Earth and whether it's similar or different to some of these other near-Earth objects. And we can start connecting what we can see from the rock to what we can see via telescopes in space. So fortunately for us at Curtin, we have a great facility called the Desert Fireball Network, which has cameras in the desert pointing at the sky, waiting to capture images of fireballs as they come in. So then we can use those images, triangulate where it would have dropped a meteorite, and then triangulate also back to what the orbit was. And we had a team out there searching for that when it was discovered.
Just so happened, hey? And how fortuitous. And for listeners who perhaps don't understand the geography that we're talking about, it was in the Wheatbelt area between the town of Norseman and Hyden. So that's in the southwest corner of Western Australia, very remote, and landed in a salt lake. So it was actually its landing spot for this particular chunk that was found was actually visible via a plane, right?
Sure. So it was captured on 2 of the Desert Fireball Network cameras. That wasn't enough to really narrow down the search area of predicting where it might have dropped to, a couple of kilometers. It was more like 50 kilometers squares, which is really big. So our team published that result to the general public to say, hey, look, if you're in the area and you find something, maybe this is where you want to look. And at the same time, the team went out and took an aeroplane and flew over the search area. And a lot of it was Salt Lake. Maybe 30% of the search area was Salt Lake. The rest of it was thick bush. So the idea was, okay, if it's hit the Salt Lake, you'll be able to see that as a disturbance on the surface real quick. And I think they spotted disturbances on a couple of the Salt Lakes. And they could see a character walking across the Salt Lake to right where they were. And this is the policeman who found the first fragment of that Mother's Day meteorite. Since then, a couple of days later, our team went back out there before the rains were about to come and found a lot more. And they joined up with a policeman who found it. It was an amateur collector who's a really nice guy. And this morning, we've been looking at those and trying to prepare those for analysis in the labs at Curtin to figure out more about it. So it's a really exciting time at the moment to figure out exactly what that rock and those rocks can tell us and link it back to these potentially hazardous asteroids that are in our vicinity of Earth and help in the pursuit of planetary defense.
Well, what a thrill to be part of such a developing story. We're right on the cusp of finding out what the makeup of this particular meteorite is. And how long do you think it will be before the results of that analysis will be made available for us to chew over?
I can't promise, but maybe we're talking off the order of a couple of weeks to maybe a couple of months. So something might come out of this, but it looks like a special one.
Will, this is just one of many exciting strands of research underway at the John Delata Centre. Are there any future missions and sample returns you're looking forward to?
Yeah, so I mean, this real renaissance in analysis of this material, I think, really, I mean, we're understanding the material, so geologists and material scientists, but we're linking that with people who are doing remote sensing. So there's ongoing missions. So the satellite that dropped off the capsule that came back and returned the material from asteroid Bennu is continuing on, and so that's going to now called the OSIRIS Apex mission. And that's going to go see Apophis, another near-Earth potentially hazardous object, and study that with remote sensing.
For those of us who are unaware, could you tell us a bit more about Apophis? How close will it come to Earth, and what are researchers hoping to learn from that near-Earth encounter?
So asteroid Apophis is going to rendezvous with Earth. It's got an Earth-crossing orbit, and in 2029, it's going to come really close to Earth, and this is going to be in between Earth and the geostationary satellite. So it's really close. So the mission out there at the moment is going to monitor as it comes through its close pass with Earth to see what happens. Does any bits come off it, or is it bringing its friends, or how is it going to be deflected by Earth? We think that it's not going to hit Earth, so we don't need to go with some deflecting kind of technologies. But it's certainly it's going to be a close miss.
Will, is there anything else we'll be looking at when this asteroid flies past Earth?
What we need to know is when we do go there, what we're going to do. At the moment, even when NASA went to Bennu, they thought they were going to be landing on a solid surface. Everything was built around, basically landing on a solid. And when they went to land on it, they're basically landing on something with the material properties like a bowl of popcorn. So you just push straight through it.
Really?
Yeah. So there's a lot we thought we knew that it was completely wrong. And so if you were going to try to do a mitigation strategy against an asteroid that was coming to Earth, and you thought it was a solid, but it was really a rubble pile of lots of small pebbles that aren't particularly well stuck together, putting a nuclear bomb in there is probably not going to work. So we've got to understand the material to help understand the mitigation strategy and test different things out.
Oh my gosh, this is completely out of my wheelhouse, boys. But you're saying, Will, that it had the I guess the consistency of popcorn.
Bowl of popcorn, yeah. So lots of sort of little balls that are only just touching each other, but you could probably put your hand straight through it if you wanted. So this the touch and go mechanism, which was supposed to just sort of dust off the surface, so to speak, end up displacing about 6 tons worth of material because it was basically so loosely held together. When it fired its thrusters and its gas collection system, it just blew all the material away because it was so weakly held together. So it shows that what we thought was there is not the case, and so we've got a lot to learn.
So in terms of asteroid properties and what we can learn from the samples and really feed back at that interplanetary defense, it's really important. We can measure the strength of this material and how that will react if we have deflection technologies and things like that. NASA in 2022 had a mission, and not many people know about this. It's called the DART mission, or its acronym is DART. It means Double Asteroid Redirection Test.
Oh.
And in 2022, it went to a double asteroid, that is 2 little rocks sort of orbiting each other. And the idea was to do a deflection test. So it fired itself, the spacecraft, into one of the asteroids to move its orbit and to see if it transferred the momentum enough to shift it off course. And this is a kind of technology that we might want to employ for planetary defense one day. And so it was the first ever test of something like this, and it was really, really successful. And it did a much better job than the scientists were predicting, and we've learned so much from that. In 2026, there's going to be a joint European Space Agency and Japanese Space Agency mission called Hera, which is going to go back to those twin asteroids and kind of look at the damage,
Right.
kind of map out the cloud of stuff that was produced during that collision, and that's going to be an exciting thing to see as well.
Will, you spoke before about the whole notion of, well, what is it that we do if something like this were to happen in the future, a possible collision? The question of jurisdiction, is there I guess, an international body devoted to creating policy on this, or are we united on this, or does it become one country's problem?
There is some international bodies that are looking at this, whether we're not united in principle. What will happen when you've got to be huge investment in money for a mission? It will be interesting, but yeah, it will require a huge effort from lots of the countries around the world to do this. There'll be people looking at the remote sensing of the object to try and understand its properties, link that with the studies such as the work that we've done on actual samples that have returned from similar types of objects. And then there'll be a suite of teams trying to get a mission to fly something to it, and then hopefully use an informed approach to kind of apply a successful strategy.
So I agree. I think it's an international problem, and it's going to require an international solution and cooperation all the way. There's just been a scientific conference actually in South Africa on planetary defense, and we had some of our PhD students from Curtin attend that, and they reported back that the conference also had policymakers and scientists talking together, which was a really interesting combination. And they were asking and trying to address the question that you just asked there. Whose responsibility is it? What if we deflected it, but it deflected to, a country that wasn't Australia? And how do we deal with things like this? They're all really interesting problems, but also just the scientific problem of deflecting asteroids and changing their course. There are some ideas out there, but only one of them has ever been tested. So it's going to require an international effort to develop more missions to test other technologies, so we can figure out which is going to be the best option. And I think most people agree that nuking them is not a good option at all. It creates lots of little ones, which it turns a missile into a shotgun.
Yes, maybe that method is strictly for the movies. Nick, you've been studying planetary samples since 2008, 2009. What do you foresee happening in the next decade or two in this field of research?
The samples that we have in hand, extraterrestrial samples, are either meteorites, which are rocks that have made their own way here, or they've been returned by astronauts, the Apollo missions from the moon, of which there were only a limited number, and they stopped in 1973. Or they're these robotic sample return missions from asteroids. There aren't that many. There's not a lot of material at all. And one thing that seems to be progressing quite well is a new era of space travel, space exploration, and we can all see SpaceX and all of the other companies accelerating their capabilities to go back to the moon and so on. So one thing that would be possible is bringing a lot more material back from these things. And one challenge that we have as scientists is actually analyzing so much material. So I think incorporating things like machine learning and automating the processes that are painstakingly manual right now would be a really, really good way that we can improve on understanding planetary materials. And the advances in instrumentation have never ceased to surprise me. I've had a longish career so far, in the geosciences and more recently in planetary sciences, and how the instruments have advanced over that period of time is fantastic. And I think talking to the instrument developers and saying what our needs are as planetary scientists to help really forge those along. It's worked in the past. We certain type of iron microprobe called a shrimp was developed specifically to look at lunar samples when they came, and we have until recently we had 2 at Curtin, two of maybe a dozen in the entire world. So it's that kind of instrument development which is really exciting, I think, in the future, plus the automation and machine learning and getting high throughput of lots of volume of samples, I think would be great.
Will, with all this progress, what's next for the centre in terms of equipment and research infrastructure?
The university management knows that high quality research requires high quality research infrastructure. So we need the tools to be able to do these great analyses. So and to attract people from around the world to use them. So the universities, building a building called a Future Sciences Building, and it's going to have a floor just dedicated to really housing these tools. So it's no point parking your amazing Ferrari in a terrible garage. If you park that in a beautiful showroom, actually the tool will not only look better, it'll actually work better. So if we want to push the limits to get better resolution, to more sensitive analyses, this is the building will allow us to do it. So we're really excited to be doing that. And it's not just having one tool. Lots of universities have a single tool that can do a really, really cool thing. But what we're building here with the centre now, but also moving into the future, is a suite of tools that can answer a wide range of questions. Not just look at a problem from one angle, is to really use a number of different probes to tell you all you can find out about a sample, and in particular things like sample return missions, when you have such a small amount of material and you really want to get the most amount of information. Yeah, we're really well set up to do that.
Well, gentlemen, these are exciting times here at Curtin and at the John Delaney Centre. It's been an absolutely fascinating chat with both of you. Thank you very much for coming in and just divulging some of this exciting material and research that you're working with at the moment. Thank you.
Thank you very much. It's always a pleasure to share whatever I get excited about. I just would love the world to see what I see.
Thank you. It's been a lot of fun.
You've been listening to The Future Of, a podcast powered by Curtin University. As always, if you've enjoyed this episode, please share it. And don't forget to subscribe to The Future Of on your favourite podcast app. Bye for now.